So after my super long video on implicit differentiation, this will thankfully be a bit shorter as we're going to start talking in this video about one of the main uses of derivatives and especially of implicit differentiation, related rates. So derivatives are all about rates. The derivative itself is the rate of change, the exact rate of change of y over with respect to x. So there is it's pretty obvious that there will be some rate problems with derivatives. Okay? So related rates problems are often applied and real world problems. Okay? And we're going to see an example of what a related rate problem looks like and how to solve one. So imagine we had a square. Imagine we have a squared. So this is our square with side length s. And with side length s. And s is constantly changing. Okay? So the rate at which the square is increasing, okay, the side length is increasing at a rate of 2 meters per second. So both of the sides are increasing with a side length of 2 meters per second. So what we want to find out is at what rate the area changing when the side length is equal to, let's say, 6 meters. Okay? So it's at 6 meters, okay? And it is increasing. The side length is increasing. So at what rate is the area changing? Okay? So how do we set up? Okay, so first, what is the area of a square? The area of a square is s squared. Okay, s times s. So we have our initial equation. We know that the side length, both of them, increase at a rate of 2 meters per second. So ds dt, basically the rate at which the side length increases changes with respect to time. Okay? So the rate at which the side changes as time passes is positive 2. And I see positive because there'll be examples where there are negative rates. And we'll do one of those later. So we have plus 2. So we want to find the rate at which area changes. So we're going to see why it's called related rates. Okay? So we want to find dA dt. So it seems quite obvious. So dA dt when s equals 6. When we want to find the rate at which area is changing when the side length is 6 meters. So what you want to do is basically use implicit differentiation to basically get the derivatives with respect to time. These are rates. So you want to differentiate with respect to time. So you have the derivative of a equals the derivative of s squared. So basically perform implicit differentiation with respect to time. So we get dA dt, okay, equals, we'll use chain rule here, 2 times s, well, I'm differentiate with respect to s, times ds dt. ds dt. And now you can see here why it's called related rates. The rate at which the area changes is related to the rate at which the side length changes as represented in this equation. Okay? So if you want to find the rate at which area is changing, then you just have to plug in the values. dA dt equals, well, 2 times, well, our side length is 6 meters. So it's a good habit to put units. And ds dt is positive 2 meters per second. So sides are increasing at a rate of 2 meters per second. So we have 2 times 6 times 2, and we get 24 square meters per second, which means at the exact moment when the side length is equal to 6, the area is increasing, it's positive. The area is increasing at a rate of 24 square meters per second, which is quite cool. Okay, so let's do another one. Okay, some of them will be quite easy, yet some of them will be a bit challenging. Okay, so we're gonna do, let's say you had a balloon. Okay, it's my best attempt at a balloon, and it's leaking out air. Okay, it's leaking out air at a rate of 15 cubic centimeters per second. Okay, so I honestly don't know whether that's really slow or really fast, but let's just say 15 cubic centimeters per second. Okay, so at what rate is the radius changing? Okay, at what rate is the radius changing when the radius is equal to 4 centimeters? Okay, 4 centimeters. Actually, not 4 centimeters. Let's make it 1.5 centimeters. Okay, so what do we do here? So we first have to find the volume equation. So volume of a sphere, it is a spherical balloon, is 4/3 pi r cubed. Okay, so 4/3 pi r cubed. So we want to differentiate with respect to time. So we get dv dt equals the derivative with respect to time of 4/3 pi r squared. Okay, so dv dt equals 4 pi over 3 times 3r squared dr dt. dr dt, meaning 3's cancel. So we get dv dt equals 4 pi r squared dr dt. Okay, so dr dt equals, we're going to divide by 4 pi r squared, dv dt over 4 pi r squared. Okay, 4 pi r squared. And if we were to substitute, now here's where you want to be careful. Well, the rate at which volume is changing with respect to time, you're going to have to put in a negative value. Why? Because the overall volume is decreasing. The air is leaving the balloon. So you have to put negative 15 cubic centimeters per second over 4 pi times 1.5 centimeters squared. And that that will equal, so if I just plug it into my calculator, we get 4 times pi times 1.5 squared. We get negative 0.5305 meter, well, not meters, centimeters. Keep the units. Centimeters per second, which means at the exact moment the radius is 1.5, the negative sign tells you that the radius is decreasing at a rate of 0.5305 centimeters per second. Okay? So you have to rearrange for the rate you want to solve with the assorted givens. So let's do one more. Okay? We're going to do more, and I'm going to do more next video. The more challenging ones. Okay, so now what we're going to do is a good old multi-step problem. Okay? Okay. So here is a corner, and this is a classic one. Okay, so this is supposed to be a wall. Okay, this is supposed to be a wall, and this is supposed to be a ladder. So this is supposed to be a ladder. Okay, the ladder is supposed to be 25 feet long. 25 feet long. Okay? And you're pulling the base of the ladder, you're pulling it at a rate at 2 feet per second. So, A, how fast is the top of the ladder moving down? So I'm just going to put V, since V is typically used for speed. Okay, how fast is the top of the ladder moving down the wall? Okay, moving down the wall when its base is 7 feet from the wall. Okay, when this X is 7. Okay, so let's call this X and let's call the vertical distance Y. Okay, this will be a right angle, so you could easily see a connection between X and Y. X squared plus Y squared equals 25. 25. So what you can do now is use implicit differentiation and take the derivative with respect to time t. X squared plus Y squared. And using implicit differentiation, you get 2x dx dt plus 2y dy dt equals 0. Okay? Equals 0. So you can cancel out the 2's from the back. You can factor out a 2 and divide it. Okay? You can do 0 divided by 2, so the 2's will go out immediately. Okay? Which means we want to find dy dt, the rate at which the top of the ladder is moving down the wall. Okay? So that gets us y dy dt equals negative x dx dt. And so we get dy dt equals negative x dx dt over y. So the base we said was 7 feet from the wall. What is y? Well, I could use Pythagorean theorem over here, okay? And if you're really good, you might see it as a Pythagorean triple, and we get 24 feet. So y is 24. So you have negative 7. Now you have to be careful about what sign you use for dx dt. X is increasing because as you move it this way, the distance x will start to get higher and higher. So we have to put a positive value. So we get, it's better if we put units. So it's better if we put units. We get 7 feet times 2 feet per second over y. So 24 feet. And we get negative 14 over 24 feet per second, which can be simplified down to negative 7 over 12 feet per second, which is approximately equal to negative 0.5833 feet per second. Okay, so that's part A. Again, you can see the negative sign, and it makes sense because y is increasing, because the top of the ladder is moving downwards. So it makes sense we got a negative sign in our answer. Okay? So there's a part B to this. Okay? So we're going to consider this triangle that's formed. So I'm going to shade it in green. Consider the triangle that's formed. Okay, let's just use blue. So consider the triangle that's formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So first you have to write our first equation. The area is equal to, well, 1/2 base times height, or 1/2 x times y. Okay? And now we have to take the derivative. Take the derivative with respect to t. So we have dA dt equals, take the derivative. I'm going to pull out the 1/2 over here just so it doesn't get cluttered in the derivative. And we get 1/2 times 1/2 times f prime dx dt g plus g prime dy dt x. Okay? So this is dA dt over here. And if we want to solve for dA dt, it's already solved for us, so that's convenient. So all we have to do is plug in values. X, so we're still talking about when x is 7 feet. The base is 7 feet from the wall. So we use the exact same value for x and y. And also the exact same values for dx dt and dy dt. Okay? So you have 1/2 dx dt, we know is 2 feet per second. 2 feet per second times y, 24 feet, plus dy dt is negative. And I'm going to use this fractional version since it's exact. Negative 7 over 12 feet per second times x, 7 feet. And that gets us, if we plug into our calculator, that gets us 2 times 24 plus 7 over 12 times 7. Don't forget the negative. And we get approximately 43.917 feet squared per second. So it's increasing. The area is increasing since our rate is positive. Okay? So it's because our rate is positive. Wait. I almost forgot we need to divide by half. So we're going to divide this by 2. And our actual rate of change is 21.958. So this is our rate of change of area. Okay? And now there's one last part. See, let's even put in here. Find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So the angle between the wall and the house. The wall and the house. We're going to call theta, since that's basically our angle variable. How can we express theta as a function of either x or y, or x or any of the given values? So we're given the base, okay? And rather than deal with y, okay, by using the tangent of theta, we're going to have to use trig here. We can use a constant factor, 25, by using sine. So let's just use sine of theta is equal to x over 25, opposite over hypotenuse. Okay? So if we want to find dt, differentiate on both sides. We get cosine, derivative of sine is cosine, cosine of theta times d theta dt equals 1 over 25 times dx dt. And we get d theta dt is equal to dx dt over 25 cosine of theta. Okay, so that's good, but we don't know what theta is. However, we can easily solve for theta using the fact that sine of theta is equal to 7 over 25, x over 25, x is 7, and we just take the arc sine or the inverse sine. Okay, so we take the arc sine of 7 over 25, and we get, we put in radian mode, arc sine of 7 over 25. We get theta is equal to 0.2838, okay? 0.2838 radians. So if we were to substitute, we get 7 feet per second over 25 feet, okay, 25 feet times cosine of 0.2838. And we get 7 over 25, or 7 over 25, or what you could have done, that's even better, rather than finding the actual angle, okay, because I just realized something. Okay, a revelation has come to me. That rather than finding the actual angle, you could use the properties of the triangle. Okay, so if you didn't have a calculator, okay, then it'll force you to think, how would you find the cosine of theta? We know the sine of theta is 7 over 25. So we know these two sides. We know we can solve for y to be 24. So cosine of theta is actually, regardless of what theta is, we are not solving for theta, we're solving for cosine of theta. That's adjacent over hypotenuse, 24 over 25. Okay? So this is also a really clever way to find cosine theta without actually finding the angle. Okay? And if we do it right, 25 times 24 over 25, that gets us, my battery's running low. Bit messy over here. We get 7 over 24 radians per second. So this is the exact change. Okay, we might have an error if we put the decimal value, but because we use something clever, okay, I almost said the dumb way. This is the smart way to do it. We got the exact rate of change of the angle, 7 over 24 radians per second. Okay, I'm sorry, this video's gone a bit long, but we're going to do more related rates problem because there's so many types of them, and plus it's one of my favorite types of problem.